Welcome to the another video of the power electronics. This is a demonstration of a practical experiment. There to fire the SCR or to give the gate pulse to the SCR with the help of a single phase cosine firing circuit. Now, where is the SCR over here? This is the SCR with the anode over here and the cathode is here, and the terminal which is taken out, this is a gate. Now this SCR, it can be turned on only when there is a gate pulse is there. And to turn off, you need to cut off this input current, or the input current by itself need to come down to 0 or below the holding current of the thyristor. So this SCR can be turned off only when the current through the thyristor is below the holding current, and it can be turned on only by giving the gate pulse. So this is one SCR. You have got one more thing is a load. It is written here is 25 watt, and if you measure the resistance between them, it is coming around 100 ohm. So obviously the current carrying capacity will be the maximum current that can flow through this load will be given as we know the P is equal to Y square R. So the value of I is equal to root over of P by R, and that comes to be around 0.5 ampere. So the current value should not exceed 0.5 ampere. So obviously we cannot give 220 volt over here, and here is a transformer where the supply input is 220 volts 50 hertz, which has been stepped down to some value, and this is called Vs. So we have here supply terminal. These two are the supply terminals. So how to make a series connection? So from the supply terminal we can connect here, and the other end of the thyristor we can take it out and connect in here, and the other end of the load we can take this out and connect to the neutral. So in this way we can have the series connection. The current will go through this, through this, through this. It will go and go like this, then it will go through the load, then it will come back with this wire and come to the neutral. So we have a phase and neutral like this. Now to give the gate pulse, here we have got or to understand the single phase cosine firing circuit, here we have got some test points. So in the test point, what happen is there is a AC reference signal is there. This reference signal is usually a sinusoidal waveform, and which is being given to the integrator, and the output is obviously a cosine waveform. So if I draw the cosine waveform integration, after that it will be lagging the sinusoidal voltage by an angle of 90 degree, because integration of sine theta is minus of cos theta. So if you draw the inverse of the cos, obviously this will be just like opposite of it, 180 degree out of phase. So it will be like 180 degree out of phase, and you can draw the inverse of the cos. In this way we can see these three waveform together. Also if you want, we can see this four waveform together, like Vs, V reference, V cos, and V cos inverse. I will show you these four waveforms. This one Vs, this one VAC, and V cos inverse in a CRO all together, four waveforms. Here it is. The volt per division of all the first supply voltage, this is a Vs, this is a 20 volt per division. After that this one is also 20 volt. These two, the volt per division is 10 and 10. So if this is a 20 volt per division, now this has zoomed up, so this per division is 20. So this is not going to cover this 40, this is like half of it. So this height is around 30 volts, and the down is around 30 volts. So I can say this Vs peak to peak is equal to 60 volts. So you can calculate the Vm is the maximum voltage is 30, so you can calculate what is the RMS voltage Vm by root 2. So this is the supply voltage Vs. Now what is the V reference? This one is a V reference. So V reference is also having the scale of 20 volt per division. So if I zoomed it up, so this is 20 and you have got some this value, so this is nearly, this will be 30, till here it will be 30, so this is nearly 25 volts, will be nearly approximately 25 volts. So you have peak to peak is 25 and this, if you take measure this 12.5 around, so nearly like this, so you can calculate what is RMS. So objective here to tell that if this is a Vs is starting from here sinusoidal, you can see the VRMS is not sinusoidal, is 180 degree out of phase. If Vs is starting from here at 0, suppose let us say this is 0, we find that V reference is intensely made out of phase. Out of phase meaning it is reverse, right? So if you just take in otherwise, if we take that this is a y-axis, if the supply voltage is taken negative like this, the cosine waveform or the reference waveform is made sinusoidal. Correct? So this is the relation between these two. So similarly, if this is a V reference, integration of that will be V cos. We can see at any point that if the sine waveform is starting from here, you have the other side, it is a cosine waveform. And this, if this is V cos, this is V cos inverse. The V cos inverse is just the opposite of it. It is going the upward direction. You can see that it's going the negative direction. In this way, we can see all the four waveforms together, right? So this is one part. So let us come to the board. So these four things we have seen: Vs, V reference, and V cos and V cos inverse. These four things we have seen now. So next we will see that if V cos is there, V cos inverse is there, there is another input supply is a VDC. This VDC, it can vary from 4 volts to minus 4 volts in the lab. How to vary this? There is a this knob is there, which here is a 0 position, so it can rotate in the anti-clockwise like this. So if it rotates in anti-clockwise, so what exactly it is doing is, if it is at this position, it is like 4 volts. If it is rotating like this up to here, it becomes minus 4 volts. So by changing this, you are actually changing the DC level from 4 volt to minus 4 volts. And this is also called the firing angle. So this is 0 degree. When you rotate this, it becomes 180 degree over here. So 0 volt corresponds to the 4 volts, or nearly to the, not 0 volt correspond to 4. This is the beginning. So it should be nearly 5 volts to minus 5 volts. If I really want to start from 0 and end it up 180 degree. Because our the sinus, the reference is something like this. Now if this is a sinusoidal waveform and if my DC signal is like this, so where is the intersection? The intersection is somewhere here. So if this line, which is a DC line, if this line coincides with the peak of the waveform, then I can start it at 0 degree and this can end up with 180 degree. That I will explain in a very short time. So now just to know that the DC level can be varying by rotating in anti-clockwise. Another is a phase angle adjustment. Here you can see the cosine waveform. If this is a cosine waveform like this, the amplitude of this cosine waveform can be decreased by rotating in clockwise. So if you rotate in clockwise, this amplitude will decrease. To understand that, suppose you have got a waveform like this. Now if we rotate it in the clockwise, this amplitude will now decrease in this way. So if now you have a DC signal like this, earlier you have an intersection over here, now the intersection is here. So you can adjust the phase with the help of this phase angle adjustment. Now another thing is here is the gate. This is where here we have the comparator 1, comparator 2. Here we have F1 and F2. So these four signals we will see together. Like first we will see the cos and cos inverse and comparator 1 and the DC level, because this DC level, or let us have a cos and DC level and see that if they will be seen together, how does the comparator 1 output is coming. So let us see that. So in this waveform you can see that there is a sinusoidal waveform is there and there is a DC line is there. So the intersection points are, these are the intersection points, right? So intersection point in the comparator 1, when this line is greater than the AC waveform, then only you will get the output. And during the time when AC waveform is greater than this, you will not get the output, you will get 0. And like that it will continue. So this is the intersection. What we observe here is that it should start over here, but it is not starting here, rather it is starting after some while. So in practical, what happened, because of the delay, you get like this. So if you have, so here it is exactly the two pulses are shown in comparator 1 and comparator 2. So here, how can we explain that? Because you have got suppose this is a V cos. What will be the V cos inverse? It will be out of phase. So if I would like to draw the V cos inverse, so this should be look like in this way. It should look like this this is a V cos inverse, right? So if I would like to find out the intersection, like this intersection, when you find this is intersecting with this, similarly this V cos inverse intersection is finding it is intersecting with this one. So we are getting one waveform, one pattern in this way, another pattern we are getting here. That means this is what we get is from the comparator 1 and this one is what we get for comparator 2. So comparator 1 is coming because of the cosine waveform and DC, and comparator 2 we are getting from inverse cos and DC. So when this inverse cos is, this is the intersection point. So after that you can find this DC line is greater than the inverse cos, then you are getting the output. When DC line is greater than again the inverse cos, then we are getting the output. Similarly, when DC line is greater than the cos, you are getting the output. DC line is greater than the cos, you are getting the output. In this way, you are getting the comparator 1 and comparator 2, you are getting the output. So, thus from the cos and cos inverse and DC, you can get comparator 1 and comparator 2. Now these comparator 1 and 2 are passed through the clock pulse, are passed through the clock pulse generator. The purpose of the clock pulse generator, this can be explained over here. Like you can see the comparator 1 over here, it will check the rising edge of the comparator 1. Similarly, the comparator 2, there is a rising edge of the comparator 2. So at the rising edge, you are getting a clock pulse 1 here, here. So this is the clock pulse 1 is generated at the rising edge of the comparator 1. Now clock pulse 2 is generated at the rising edge of the comparator 2. This is here. So we are getting at the rising edge of the comparator 2, we are getting a clock pulse 2. So these clock pulse, what we get, So these two clock pulse 1 and clock pulse 2 are fed to the JK flip flop. Like if the JK flip flop is there, so JK, the two in and output will be Q and Q bar. So J will be fed to the clock pulse 1, K is clock pulse 2 is fed to K, clock pulse 1 is fed to J, and that will give output as Q and Q bar. The whatever JK flip flops 1 is output is what we are getting is you are getting a pulse like this, and at one clock you are getting a rise, another clock you are getting a fall. Again at one clock you are getting a rise, another clock you are getting a fall. And if this is a Q, the Q bar will be just a complementary of it. So you're getting a Q bar. And in this way you are getting the two clock pulse over here. So you are getting here the F1 and F2. So these clock pulse, what you can see here, the clock pulse like this, they will pass through a pulse transformer to generate a pulse during the time it is high. So these pulses, what we get, can be obtained from the gate and the cathode, from the gate and the cathode common terminal. So these pulses can be available over here. So if we connect this and this, we can turn on the thyristor, and when the pulse is low, we cannot guarantee that when the pulse is low the current is zero. The current can be zero only when the current input supply voltage is zero, or the current through the thyristor is below the holding current or zero. I will explain you that another video, that how does the input waveform is related with this output voltage and the gate pulse.